So for our third and fourth exercises, we're actually going to be using kinetics data for our third exercise, and then our spectroscopy from our FPLC purification data for our fourth exercise. So I want to show you where you'll find this data first. So again, under Learning Units, if you go to our data misinterpretation lab, you'll see here at Data Files, Lab Data for Bootcamp. So that's the data file you're going to want to download and use. And so let me head over to where that is here. So this is a workbook that has 3 worksheets in it. So we're going to have some raw kinetics data and then some kinetics velocity data that'll be used for our third exercise, which is this video. And then our last exercise will be our double Y data. So I'll have a separate video for that. So first, let me go ahead and change so we're not squinting here at the screen here. So this is like the data we'll get from doing our kinetics experiment off of the spectrophotometer. We're basically going to be measuring a time course, so taken every 10 seconds over a course of 4 minutes here with this data, and measuring the absorbance. So just bear with me a little bit as I read through here to just kind of make sure I highlight the important parts of what's important with this skill. We call this third time's a charm. So we often obtain scientific data from experiments in triplicate, meaning that we're going to perform the experiment 3 times. So again, we're going to talk about some additional aspects of this in our biochemistry boot camp. You guys have already done that. It's, again, you get precision by repeating experiments. We'll talk about how we think about accuracy in a little bit here. So for now, we're just kind of simply considering how data acquisition as data times 3 relates to what we'll do in Excel. So not anything to deal with the precision or accuracy components with this lab. We're just learning how to use Excel to analyze our data. So in this exercise, we're going to learn how to plot some data and then importantly put error bars on. So using the data on the first worksheet, which is our raw kinetics data, we're going to plot absorbance versus time. We're going to fit the data to a linear trend line with an equation and an R-squared value, and then the slope of this line is actually going to tell us the rate of the reaction. So you guys have actually already done kinetics, so you sort of understand this, but just kind of highlighting what we have here is we have measured the appearance, in this case, of a colored substrate over a 4-minute time course. So anytime you're measuring the change in something as a function of a change in time, that's rate. So this is a change in absorbance, which again, that's a proxy for concentration through Beer's law. So this is a change in concentration as a function of a change in time. So this is the rate of the reaction as measured by a change in absorbance. So we can just basically select this. We've already in our last exercise kind of learned how to create scatter plots. So we're going to do a scatter plot here. So here's our scatter plot with our data. Again, selecting one of these data points, we can add a trend line. Okay, so we're going to do a linear trend line. We're going to set, or we're not going to set the y, we're going to display the equation and the R-squared value. We don't want to set that y-intercept to 0. You saw what happened here. Let's just toggle and see there. We don't want to set the y-intercept to 0 because our data doesn't start at 0. You might remember when you did this kinetic experiment, the experiment was starting as soon as your pipette hit that cuvette and added your enzyme to it. But then you needed to mix, then you needed to put it in the spectrophotometer, and then you needed to click start. So there was a lag time. So in reality, the start time for this experiment is like minus a number of seconds here. But we could actually, back calculate, if you will, here, and we could find out, that's an interesting little thing, right? Back calculate, draw this back out to see where you intercept the x-axis here. It's going to be a negative number, but that tells you how long ago that person added the materials and started the reaction. Interesting. All right. So here's the information that's important here. Again, we've got a rate of the reaction that we have here. Now we'll get into some more weeds with the actual kinetics experiment when we kind of look at some videos for how to analyze that data. Remember, this is absorbance units right now. We actually want to convert that to concentration, so we'll talk about how we do that when we analyze our kinetics data. We need to have the extinction coefficient for whatever we're measuring, because remember, absorbance equals the extinction coefficient, that's that epsilon, times the path length, that's B, times C, which is the concentration. That's Beer's law. Path length is always 1 in the cuvettes that we have. So if we know the extinction coefficient, we can directly connect an absorbance value to an actual concentration. So we'll do that in our kinetics lab. Not important for what we need to do here. So this is actually how we get the rates of the reaction. Okay, what we're going to do now is use this velocity data. So here you can see that's where that piece of information is. This actually was from, and you guys didn't experience this when you did this, this was kind of the background rate of the reaction, because this is when we had no substrate in there. Let me make this bigger here. So this is when we had no substrate. There was actually a little bit of a background reaction here. Okay, but this is looking at increasing the concentration of substrate with our enzyme reaction, and then as we'd expect, the reaction gets faster. And we did this reaction in triplicate so that we could kind of see what was going on and check our precision. All right, so the next step says using this second worksheet, which is our velocity data, and it has that data point there, average the 3 trials of data in the adjacent cell for all 6 substrate concentrations. So we're going to use an equation for that. We can say equal average. Now, you can put in parentheses. I'm going to show you 2 ways to do this. You could say parentheses, and I'm going to say I want to go from B to, and then I put a colon, D to, and then I close. You can see it highlights those cells that we're interested in. So that's one way to do it. I also could say equals average, and then I could select this cell, and then I'm going to hold down the shift, and I'm going to come over here. That's another way that you can select that. Okay, I can also say equals average, and then again come over here and just drag. Oops, that didn't work. Equals average, and I could select this guy, and then I could drag over. So rather than holding the shift key and then selecting, I still need to put my parentheses in and kind of do that. So all ways of kind of calculating the average. And because this is the same equation essentially, I'm just going to finish out the rest of these by dragging down. So that gets the average of those. That's the data that we're going to plot. We don't want to plot our individual trials. We want to plot the average of them. We're also now going to calculate standard deviation, and we're going to use that to create the error bars on this average data point. So again, the standard deviation shows how much these 3 trials worth of data deviate in a positive and negative sense from this average. So there's lots of different ways you can think about doing error bars. We'll see them when we go to put them in here, but we're going to use the standard deviation. So, and I'm going to highlight here that we're using standard deviation .p. There's different standard deviations, but because of the kind of data that we have here, I'm not going to get into the weeds as to why. I can talk offline if anybody's interested. That's the kind of standard deviation that we're going to use. So to calculate standard deviation, I'm going to say equals, and you can just start typing STDEV. We can see all the different kinds of standard deviations. We're going to use the .p, and it says, well, what do you want to include in that? And I want to say these guys. So all of those different ways that we could kind of select those cells, we're going to do that. And then I'm going to copy and paste this down. So I'm going to pull that down. So that calculated the average of that data and then the standard deviation. So now we're going to prepare a smooth marked scatter plot of the average velocity versus the substrate concentration. Okay, so another trick I'm going to show you here. Right now my substrate concentration is all the way over here on the right, and there's all of this data in between that I'm not interested in. So if I tried to select this and then kind of come over here and select this, right now it changed what I selected. I didn't select anything. If I come over here and select this and then I use my shift key and come over here, it's going to select all of that. So again, we needed to find a way to select columns of data that aren't kind of near one another. So here's how you do that. You can select the substrate, and this is a Mac, but I'm going to select the Command key, and then I'm going to select this. And it allows me to select 2 columns of data that aren't next to one another. Okay? Excel is always going to take my leftmost column and consider that to be your X value, and then whatever's on the right to be your Y variable. And we showed you in that last video that we just did how you could actually change your X and your Y, so if they weren't set up correctly. So again, we're going to insert, and in this time we're not going to be fitting our data here, so I'm going to choose a smooth marked scatter plot. So that's this guy right here, a scatter plot with smooth lines and markers. So I'm going to choose that, and here is what our kinetics data looks like. Now you guys have actually done enough with kinetics data that you can recognize and understand, oh, that makes sense. If I increase my substrate concentration, my reaction gets faster. It's going to begin to slow down as I begin, to get to sort of the maximum velocity. I shouldn't say slow down. We've reached the maximum velocity because we have sufficient amount of substrate there such that we can begin to approach. Now again, we'd have to have really high concentrations of substrate to get out to the maximum velocity, but that's why it starts sort of leveling off there. All right, so that was next step, prepare the smooth marked scatter plot. Now we need to add error bars. All right, so to add error bars, we are going to select our data here, come up to Add Chart Element, and then we are going to add error bars. Now, unfortunately, and I've Googled this and tried to find answers to this, by default, it adds both horizontal and vertical error bars, which I don't necessarily understand why. Usually you think of having error bars in measured data, not your manipulated data. So I'm not certain why the default is that we have them here. Also, the default is that it puts these error bars in to be a fixed value. So here we can see that fixed value is plus or minus 1, which I have no idea why that's the case. It kind of makes no sense. We are going to choose a custom error bar here. So we're going to specify that for these 6 data points that we have here, the plus and minus values are going to be our standard deviation. So I'm going to say specify value, and it's going to come up here. Right now you can see that the value is essentially a 1. So I'm going to say, no, I don't want that for my positive value. I'm going to have this. And I'm actually going to copy and paste this because I want the same values for my negative error bars. So when I do this, it changes it, and we can see what we have here, right? We've got fairly good error bars with this first data point, and then they get a bit larger with these later data points. Now, the only way that I've been able to see online that it says that you could actually delete error bars is to physically sort of select them. Well, I guess we can only go 400 here. I don't know if I'm going to be able to get in small enough here, to select those because my markers are so big. So it just might be something that unfortunately we can't get rid of. I think if I get rid of that, yeah, I got rid of my data. That's just really unfortunate. That's something new that I've noticed, that I don't have the ability to kind of select. So, we can select these, but for some reason I'm not able to select these X error bars. So it's just going to have to be what it is right now. If anybody's able to figure out kind of how to get rid of the X error bars, please let me know. This appears to be, with this latest update to Excel, something that's problematic here. All right, so we've added our error bars. And now we want to use this same data, and we want to prepare a curve that is our double reciprocal. So this is 1 over velocity versus 1 over substrate concentration. So I've got a couple of notes here. It says to manipulate your data, first take the reciprocal of each initial velocity point, and then average those values and generate standard deviations. So let me highlight what I mean here. What I don't want you to do is basically just take 1 over this guy, 1 over this guy, and 1 over this guy. We got into the weeds one year with the math about kind of order of operations and kind of why it won't actually give you the same data as going through how I'm doing it, but here's what I want you to do. We're basically going to recreate this data plot, but now as the 1 over situation. So now I'm going to have 1 over substrate concentration. Okay, and I can just have my trial 1, trial 2, trial 3. I'm just going to copy these here so I don't have to retype those. And then I'm going to have my average and my standard deviation. So now we cannot use this first row of data here. This first row of data has zeros in it. We can't take 1 over 0. So we're only going to have 5 data points for here. So I'm going to start with this guy. So I'm going to say 1 over this, okay? And oops, equation 1 divided by this guy, okay? Now, I'm going to copy this over, and then I'm going to copy this down because it's essentially taking 1 over all of that data. So it's really not that much extra work to have to do it this way, but then again, we're going to average this. I'm going to come up here and I'm just going to say, you know what, that same average equation is going to work here. Notice when you select a cell here and you come up here to where the equation is, if you select up here, it'll show you sort of the data that you're selecting for that. So I know that I'm selecting the right pieces. Again, I'm going to kind of draw this down. Same thing for standard deviation. I can copy and paste, and I can draw this down. And very quickly, I've created this next set of data that I need for this experiment. All right, so let's see, use the same data, prepare a curve of 1 over velocity versus 1 over substrate concentration. Okay, so now we're going to do the same thing. I want to create a plot here. So I'm going to say 1 over substrate concentration, and then my average data here. So I do the same thing here. We're going to insert. And in this case, I'm going to do, does it say here, did I tell you what to do? I don't specifically tell you, but I'm going to say let's make a scatter plot here, because as we can see here, the purpose of doing this is I'm creating a straight line, or I'm creating data that can be part of a straight line. So I want to be able to fit this to a linear regression, so that's why I'm plotting it this way. Okay, so let's go ahead and do the same things that we've done before. I'm going to select this data, and I'm going to add error bars. So I need to do my specific error bars, right? Don't want to have those. Now this one we might actually be able to get rid of these horizontal bars a little bit more easily. So, but let's go ahead and choose a custom value for, we can see here right now that the error bars that are selected are our vertical error bars. So we're going to have our standard deviation again. I'm going to select and copy, select that and paste that here. Okay, and so now we have those error bars. Now, these are actually large enough that I can get rid of these here, so that's great. That's good to know. Okay, last thing I'm going to do here, and it actually doesn't say to do this, so I'm okay if you don't do this, if you just kind of leave it as a straight line. But I've selected that data. I'm going to add a trend line. I'm going to add a linear trend line here, and again, I need to format my trend line. That option didn't come up here to display my equation and my r-squared value. So it's actually not an awful straight line in terms of the data points that I have here. But look at this. Look at what the error is in that data piece there. So, you know, clearly if this data point, remember what error bars really represent? They represent for the data that you collected, any of your data points could fall within this line and still represent what your data set is. So we've got a lot of potential error here. If I take this blue data point and I move it all the way down here, I'm not going to have a very nice r-squared value. Okay, so what it looks like is it's a good thing that we did 3 sets of data, because they averaged out to be something that made a fairly decent straight line. But that's a good thing we took 3, because there's not a lot of precision between that data. All right, so, and one of these things, and again, I have to remember for you guys, this is normally a data analysis. This is a lab that comes much sooner in the semester, so we haven't talked at all about kinetics. So it's just really getting us to think about this. So it says, question is, what is different about this plot and why might it be useful? I think I got ahead of myself there, that you're supposed to sort of just look at this and say, hey, maybe this is a straight line. Maybe I can get some information about it. It says, what experimental variables can we obtain from this data? Specifically, how would you obtain them from a plot like we prepared above? It says chapter 12, we're not using that textbook anymore. This is kinetics. So it asks you to look in your kinetics chapter and try to find plots that look like this. And then the last piece is, and we sort of addressed this just in chatting here, do you think small error bars mean data is accurate? What do we think about error bars? Are they really reflecting accuracy? Okay, so that represents the end of thinking about how to plot data here and generate error bars.